The particle theory is matter's made up of particles. There's spaces between particles. Particles are moving. Different substances have different particles. That's the particle theory. Kinetic molecular theory, do you know what kinetic means?
Moving.
Moving. What's a molecule?
Moving atom.
Say that again?
Moving atom.
Moving atoms, but the atoms are traveling as a group, right? 3 atoms in water, right? So they're a group. So they're constantly moving. So basically, kinetic molecular theory states all substances are constantly moving. All substances are constantly moving. There's 3 types of movement. Rotational, you're spinning. Vibrational, you're vibrating in spot. And translational, you're moving in a line. Okay? So there's 3 types of movement.
What was the third one?
You've got vibrational, rotational, and translational. That means you're traveling along a path, like you're going somewhere. Okay. Are the types. Am I standing in front of the... Let me move. Okay, 3 types of movement. Which type of particles do you think have the most kinetic energy? Which type of particle? You think they've got the most kind of movement? Can they move? Can solids move in a line? Did you say a mullet? Okay, but what's propelling that bullet?
Gas.
Gas.
Gas is
Yeah, so they have the most space to move.
Yeah. Solids have the least kinetic energy. Gases have the most. Gases have the most. Greater spaces between particles. Now, can a gas particle collide with another gas particle? What do you think?
Yes.
Absolutely. They can bump into each other. We say collisions are elastic. Not that they will pull back right away. Elastic in the terms of energy is conserved. If they bounce into each other, they will bounce apart and they will have the same energy they had before. So they're elastic. If the particles have enough energy to start with, when they collide, a chemical reaction can occur. When a chemical reaction occurs, bonds are broken and new bonds form. When a chemical reaction occurs, bonds are broken and new bonds form. So you have to collide with a particle with enough energy to actually overcome covalent or ionic bonds, and then you can reform bonds. Reactions can happen in the solid phase, liquid phase, or gas phase, but they happen faster if they're in the gas phase or the liquid phase. If I had two solids and I mix them together, you will wait a long time for a reaction to occur. If I mix two solutions together, if I've dissolved them in water, the reaction will occur a lot faster. You don't have to have all the clues happen, nor do they necessarily mean a chemical change has occurred. So we've got color change. Matthew? Energy release. So it gets hot, or you see light, got color. Smell. If you smell something, what state is it? Gas. So we get a gas made, gas formed. So you smell something new.
Oh, bubbly, is that one?
Yeah, that's bubbles. Bubbles of what?
Gas.
It's gas. It's easier to see gas being formed if it's actually in a liquid, because then you see the actual distinct gas bubbles. So energy released, so that's heat or light, gas formed. We saw it when we mixed our when we mixed our sodium hydroxide and our copper sulfate, our copper 2 sulfate.
Solid forms into it.
Yeah, a solid forms when you mix two liquids. And we call that solid a precipitate. A precipitate. Do I need to spell it? I don't mind, but it means I have to move to the next slide. Called a precipitate. In university, I developed my own shorthand because I can't write down every single word a professor says. So sometimes I put PPT, precipitate, or PCT, precipitate, PPT. Two elements form a compound. Or two simple compounds form a complex compound. So it doesn't have to be just two elements. The general formula is A plus B makes AB. Sodium plus chlorine makes sodium chloride. Bless you. Right? You've got two elements making a compound. Photosynthesis is a good example of a synthesis compound. Carbon dioxide plus water makes sugar. Is a byproduct of oxygen as well. But carbon dioxide, water, makes a more complex compound and another simple product. So this is an example of synthesis. Opposite of synthesis. So you have a compound breaking down into elements or breaking down into another compound plus an element. So a compound goes to two elements or an element and a compound. But there's one thing that is needed for decomposition that is not needed for synthesis, and that is a form of energy. So energy is required. It might be electricity. You can do electrolysis. It might be heat. But you do need a form of energy in order to have, thank you. But you do need energy to break something down. An example, potassium chlorate. Any chlorate. You will form an ionic compound and oxygen gas. You got 2 minutes. This, we've got an OH here, we've got a CO3 here, we've got a CO3 here, and really our H2O is HOH. We've got an OH here. If you treat your polyatomic ions like they were an element and follow the same rules, you should end up with the same results. Okay? So, I said do oxygen and hydrogen last. Okay. Just stop whatever you're doing for 2 minutes. 2 minutes. 2 minutes. Okay. Okay. So, aluminum does not contain oxygen or hydrogen, so let's do that one. Aluminum, there's 1 over here, there's 2 over here. You got to put a 2 over here, correct? Now, let's take a look at the carbonates. You've got 3 over here and 1 over here. So what do you have to put? You got to put a 3 here. So I've just balanced my carbonates. So I've got 2 aluminums, 2 aluminums, 3 carbonates, 3 carbonates. Now let's take a look at what's left. How many OHs do I have on the left? I've got 6 OH minuses on the left, and I've got how many H's? I've got 6 here. How many? What's the number I have to put out front here then to make this balance for my OH?
3.
No, because I've got 6. So you have to put a 6 out front here. And you're done. You will, when you have an acid and a base, when you've got a compound with an H at the front and a compound with an OH at the back, you are going to end up with the same number of OHs and Hs on the same side. Always. And they will make that same number of waters on the right. Because that is your net ionic equation for an acid-base reaction. You will end up with H plus and OH minus come to H2O. Okay? So if you treat these, instead of treating the carbonate as a carbon and an oxygen, if you treat it like it's one entity that you need to balance, I could make that a Z. I've got 3 Z's on the right. So I need to make 3 Z's on the left. Okay? You're treating it like it was one letter. That's how we did it yesterday. Over here. Is that the only place calcium is? Okay, so then that's where we're going to put our 3. Okay? So now we've balanced calcium. It's a good idea to do these using pencil because you might have a time where you have to go back and change a number that you've already put in. So now I'm going to look at the compound containing the calcium on the right. What element other than oxygen and hydrogen is in that compound? Silicon. So how many are now on this side for Si? 3. So go back to the other side, balance for silicon. So how many SiO2s am I going to need? Wow, that was a deafening 3. So now I've balanced silicon. Okay? So that leaves me with, well, let's do oxygen. We got lots of those. How many oxygens do I have in the first compound? The first compound that's on the board. How many oxygens are there? There's 8. How many oxygens are in the next one? 6. So that's a total of 14. So how many do I now have this first compound on the right? We're still doing oxygens. 9. How many more do I need?
1.
I've got 8 plus 6, 14 over here. I've got 9 here. How many more do I need to get 14? I need 5. So I'm going to put a 5 here. Now, I've got 14 oxygens. Mario.
You got another page of these?
Yep.
Like, that aren't like this? I mean, like, that are like this, just not these same ones?
You would like another page of practice questions?
Yeah.
Absolutely. Okay.
Thanks.
You're welcome. Okay, so now we've got 5 oxygens, 5 carbons. So we're balanced for oxygen, balanced for calcium, balanced for silicon, but now we've got to go back and balance for, am I randomly picking the elements that I'm balancing for? Do you think I'm just randomly picking this? Because if you don't see the pattern that I'm doing, it's going to seem like it's totally random. If you think it's totally random, you don't know where to start when you have a tricky question. So I'm going to ask you again. Do you think what I'm doing up here is random in your mind right now? Or do you see the pattern that I'm picking? You see the random. You see the pattern. Do you guys see why I'm picking what I'm picking in the order that I'm picking it? Be honest. No. Okay. I first picked calcium because it's a metal. But this compound also contains silicon. So I did that next. Because I put the 3 here, so then I did Si. Once I did Si, because I put a 3 there, I've changed my oxygens. So that's why I did oxygen next. When I put the 5 here to finish off oxygen, it's with a carbon. So I picked carbon next. So whatever is in the compound that you just put the coefficient in front of, you're picking something from that compound now to balance. So the first thing, I did calcium. So here's a silicon, so I did silicon. I did silicon, so now I did oxygen. Did that, put my coefficient in, there's a carbon there. So now I pick carbon. It's not random at all. It's a process. Calcium, calcium, silicon, silicon, oxygen, oxygen, carbon. Now I'm going to balance carbon. So I have to put a 5 here. And now I've got one last element to balance. Phosphorus, and how many do I need?
2. Basically just cut mine in half.
Up here, 2 here, so I need a 2 here, and we're done.
Mine is basically just double that.
Double it. If you end up and you've balanced an equation and you can divide by 2, or you can divide by 3, do it. You want the lowest common multiplier, okay?
Well, I'm not wrong, I'm just not right here.